Transitional presentation from the one we just heard, because around all those chromatography columns and continuous processes, you really need sensors. So that's the kind of focus of this presentation. So this is an overview. We have information just on our company, and then it gets right into the single-use sensors for bioprocessing, both inline and those that can be installed directly on containers, which becomes more important in bioprocessing. What does single-use mean? Build some confidence in that terminology when it comes to sensors. A qualification approach that could be used for any sensor if you're thinking of implementing it to a process. And then single-use sensors for continuous processing and how you implement them, and then a conclusion. Just a little on our company, even though the focus today is on the sensors, we also offer a full line of purification development systems that help develop and optimize a process for scale up to GMP. So jumping right into the sensors, the focus of today's presentations is on sensors for pressure, temperature, conductivity, which includes a temperature measurement, absorbance, turbidity, and fluorescence. The absorbance, turbidity, and fluorescence can kind of be all lumped together from a sensing technology to some degree, because they use the same type of product contact element. And there's some pictures of the sensors here. So a lot of people hear single use and they kind of think of like a paper cup you may drink out of, and it starts to kind of fall apart during its short time of use. That doesn't mean it when it comes to sensors. They're very robust, and we'll look at the materials, and they're extremely durable, even though they're not stainless steel. It's more related to low cost, minimizing the cost of disposable, which minimizes your cost of goods. By design, minimize as much as possible the product contact element, so you can recycle as much electronics as possible. And the manner of use, the sensor should not require calibration. What you don't want to do in a clean, potentially sterile single-use process is have to introduce fluids for calibration or standards that could potentially be contaminating. Sensors can be used throughout all the different bioprocess operations, from a bioreactor all the way up through final fill and finishing. We just saw a big application, obviously, is chromatography. If anyone's interested, on our website, we have key applications and in areas where sensors can be very useful and critical. In terms of the general user requirements, you want to look at fluid contact materials to make sure they meet the general standards of use, class 6, etc. You want to look at performance. This is what really separates a sensor from a piece of tubing or a fitting, is it must perform. The sensor manufacturing environment, just like other single-use components, it can introduce contaminants from the manufacturing, so it needs to be made in a controlled environment. The process compatibility, this is mainly related to solvents. Even though your process may not contain any harsh solvents, some of the preparation steps may, such as sodium hydroxide. Compatibility with sterilization bioburden reduction. From our experience over the years, this has been the death of many single-use sensors. They can't stand up to the requirements that may be put upon them here. In control system integration, that's very important for both batch and continuous processing, getting the sensors to report up to the higher level systems, which is basically the essence of Industry 4.0, if anyone's heard that terminology. And of course, regulatory approvals depending on your geography. As far as the fluid contact materials, these are the main checklists. So again, this would apply to our sensors or any single-use sensor. So this can be used as a matrix to evaluate a new technology before you spend time in the lab working with it. It should meet the proper biocompatibility and toxicology. It should have no risk of BSE, TSE contamination. And there's a quick guide to look at the materials and its compatibility of gamma before you start to proceed. And it's called the AME Technical Information Report 17. In terms of performance, you have to make a sensor meets your requirements in terms of range, accuracy, etc. And that could also be during a preparation step where it may be exposed to higher pressures or higher temperatures. Sensor manufacturing environment, this would apply to really any single-use component, must be a controlled environment with a quality system in place. And process compatibility, the sensors must be, again, compatible with all solvents used in the process, whether one with the product or one for conditioning. An initial step is to look at chemical compatibility. Later, as you move into the clinical trial phases, and of course commercial, leachables and extractables is pretty much required. And there's an organization called the BPI that set out the testing standards that's been adopted by most of the end user companies in the industry for leachable extractables testing. But again, you have to look at all the parameters such as time, temperature, and then also you don't want to introduce a sensor that might restrict flow, damage cells, or create large back pressure. Again, sterilization bioburden reduction treatments can be very harsh on many sensors. And control system integration, the sensor should have the ability to connect upwards into a local controller, a SCADA system, and then the higher level systems above that. Some manual processes can use more of a paper batch record and just read a monitor, but ideally you want to have the ability to grow. Again, regulatory approvals such as CE. So being that continuous process is more of a worst case scenario, that's kind of the focus here, because the batch processes tend to be hours versus days. So when you look at continuous processing, you really need to look at the time and type of exposure over that lengthy period of time. And the second bullet's one of the main things, is susceptibility of drift. What you don't want to do at the end of your run, find out there was a big drift, because then your data is potentially suspect. And what's kind of interesting is things have gone to continuous. Everyone wanted bigger sensors. Now everyone wants smaller ones, because you want to have a critical velocity flowing through a sensor. So a lot of these continuous processing are using 1/8" ID tubing. So just to give a little information on the robustness of materials, again, this could be adopted to any sensor. These are the sensor materials of the 4 sensors we're focused on here: pressure, temperature, conductivity, and absorbance. So you have a main contact material, which is about 95+% of the surface area, and then you have the others, which is mainly the sensing element. So we break these down by the main contact and the other material, and just look at these just based from a material perspective. And here's a summary of the different materials. And these are just some comments, and again, they're all extremely robust materials. Polycarbonate, polysulfone are used in very, very high performance applications, and they're also used in military applications, bulletproof glass, car headlights, eyeglasses. Polysulfone is actually even a more robust performer with higher temperature compatibility in polycarbonate. And dielectric silicone is extremely durable over time. It's used in a lot of medical devices that need long-term operation. The adhesives, we use acrylic light cured adhesives. You got to make sure the adhesive doesn't get attacked by any solvents or chemicals. The adhesives we use are used in long-term, again, medical applications, dental applications, and once it's cured, it's very inert. And stainless steel, everyone knows that's a very durable material. And fused silica glass used in the optical sensors is superior to any other type of glass due to its high level of purity. And of course, it can be subject to shattering, but other than that, it's a very durable material. I'll kind of bounce through these, and I can provide more information afterwards if anyone wants to know more about the technology. But this is just mainly to give you an idea of the durability of the technology doing the main sensing measurement. So in our pressure sensors, there's what's called a MEMS chip, and it was one of the first MEMS technology available on the market over 20 years ago. We've improved it and refined it for bioprocess operations, and basically is a micro diaphragm on a circuit that changes resistance, meaning piezo-resistive, as its pressure changes. And the stability over time, we haven't seen any observation of drift, and we have some data to back that up. So we held 12 sensors with air pressure for 93 days. We looked at the data periodically and recorded it. At the end, the pressure was removed, and we particularly were interested, did they go back to zero after that extensive period of time? So this was the min and max temperature that was recorded over the 93 days. So they all were maintained with pressure around 10 psi. And this is the data after the 93 days. The important data is shaded there in the first column on the left. You'll see they all pretty much went back to zero after 93 days, which is very important. And then when tested with the calibrated gauge, they were all within specification. So there was no drift of zero or no drift in accuracy. The temperature in our element's called a thermistor. A lot of people are familiar with an RTD, which is a precious metal junction. An RTD is a silicone junction. It performs very similarly and has a good response time. It just has a much more narrow range, but that's fine for bioprocess applications. And it's been documented to be extremely stable over time because it doesn't really undergo any changes. Conductivity is measuring a current across the electrode electrical potential. And there was a little less data available because a lot of people are calibrating conductivity sensors on a regular basis as they use them. So each conductivity cell, because they're slightly unique in geometry, have what's called a K factor. And so we looked at a certain K factor that gave it accuracy. We looked at the testing over time, mainly interested in drift. And we did see a slight upward drift over 30 days, but then we realized when we did our final measurements, there was actually some slight evaporation, which concentrated the salts. And upon second testing, we realized they actually hadn't changed. So that built us up a lot of confidence. There's more testing going onwards for that. And again, conductivity is very important, chromatography and filtration operations. A lot of people are familiar with absorbance. That follows Beer's law. It's a function of concentration over a certain path length at a certain wavelength. And by the time you get to the process scale, the assays are pretty much developed. You're just doing your measurements. So again, the main thing we were looking at was drift over time. And just to touch on the fact, we use an LED light source. It has a lifetime of 5 years or more. So it's ideally made for continuous processing without worrying about failures or heat up, et cetera, over time. So as long as the glass remains clear, you should be getting the same measurement. So the top picture shows the flow cell, then you can connect to fiber optics and there's glass in the wall, so the instrument never touches the flow path, only the flow cell, including the glass on the wall. And we tested this over time. We were looking for, again, a lot of these application notes were done for customers wanting to use this in continuous processing. They came to us for data. Some data we had, some we did. So afterwards, standards were put into the photometer, and they all measured accurately, and the drift was below its spec of plus or minus 0.1 AUs over 93 days. As I mentioned, there's a lot of focus on single-use continuous processing in the biopharm as well as cell and gene therapy, where they're using a lot of small-sized tubings in different process setups. So we went on to develop small sensors for the 1/8" ID tubing for pressure, temperature, absorbance, and then also more recently, a lot of continuous processing has containers for intermediate storage throughout different process steps, and people want to get data from those bags. So we again developed these new tools. We now have sensors where there's a port plate that can be sealed to a bioprocess container, and you can get measurements over time. And we have conductivity, pressure, temperature available, and we're working on some of the absorbance, turbidity, and fluorescence applications. So again, this makes a bioprocess container a smarter container. Obviously, some of these sensors exist around the bioreactors, but we're looking at more downstream purification steps. So one important thing in any single-use technology, whether it's batch or continuous, is again not the need to calibrate. So these are key implementation topics. You don't want to have any calibration required. So for each one of our technologies, we have a means to eliminate the need for calibration. And the pressure and temperature manufacture tight tolerances, so essentially each one of them are the same. Conductivity, we predetermine the K factor, so the user doesn't have to account for uncontrollable differences in the conductivity cell geometry. And then absorbance, we manufacture the path length to tight tolerances. And the other topic then is ongoing verification of monitor performance and then control system integration. So again, we touched on these. Our sensors are manufactured at tight tolerances and all 100% inspected. And then we also can deliver a NIST certificate, and they all come with a certificate of quality. Temperatures, also manufacturer tight tolerances. There's 3 temperature test points done in manufacturing to confirm accuracy. The conductivity, the temperature sensor undergoes the same process as just described, and each one of these conductivities sensors are tested with a range of buffers up to 100 millisiemens, and the optimal K is determined, it's printed on the tag, and the user enters that K factor. So each one has its own unique individual calibration. As far as the absorbance sensor, again, it's really control of the path length and make sure the quartz glass has not been contaminated during the manufacturing process to make sure it still has its full clarity. And there's a separate method to test the monitor itself. So single-use sensors really create a paradigm for metrology groups, which are used to traditional sensors. But single-use sensors, you really, in most cases, are breaking it into 2 separate elements, a monitor and a transmitter. So metrology groups feel the need to maintain their monitors even if there's no sensor connected over time. So we have tools, and any manufacturer should have tools to be able to test the monitor periodically to make sure it's still doing the proper measurement. Because the sensor may come in with a calibration cert, et cetera, but you got to make sure the monitors, and of course you can do a full loop check on everything, but for the different sensors we offer for pressure, we have a couple tools. Temperature and conductivity are just resistance measurements, and for absorbance we have testing standards, which are basically light filters. As far as control system integration, any monitor that you may use should have different types of outputs available, whether it's digital or analog, to transmit to a higher level system. This is the back panel of one of our monitors. It has digital output as well as analog output. So there's a lot of information on this slide, but the main thing is the sensors are down at this lower level here. The sensors could be on their own connected to a monitor. They could be on a bioreactor connected up to a process instrument. But the whole thing, particularly with continuous processing and sensors, you want all your sensors to be able to report up to a centralized controller through different application layers, which are kind of like your languages, Modbus, Profibus, all different types of application layers. So when you're looking at different technology, you should make sure to have these available features to talk upwards through some sort of physical layer to a centralized controller, because particularly with continuous processing, you want to be able to monitor the whole process. So you have to be careful when you're looking at devices, can report up to a controller, which is typically connected to a SCADA system, which typically goes up to a historian, which typically goes up to electronic batch record, and even to higher level business systems. So when you're making a decision, that should be an important factor. And a lot of people have heard the term the Industry 4.0. It's actually really about sensors. It's all sensors and the field devices reporting up to a PLC and a SCADA, up to production level systems, and really up to the company level, because you can't really make decisions on valves and pumps, et cetera, unless you have data and information to do that. And so that's, if people have heard the term Industry 4.0, it's the fourth industrial revolution with really sensors on everything. So in conclusion, single-use sensors are very robust technology to be considered for qualification GMP process are currently being used by many companies in the industry. The qualification data may be available to help you implement a sensor. You still may need to do some of your own testing, but you should look for a validation guide. Any technology must still be qualified for specific use to make sure it's going to perform as required, particularly in a GMP process. Metrology groups, as well as just good business practice, you should periodically monitor, check your monitor that's reading the sensors alone without the sensors connected. You should make sure the sensors can be read locally as well as be integrated to higher level systems, and the sensors are critical to Industry 4.0. And thanks everyone for listening. I'm not sure if there's time for any questions.
Oh, there's always questions always time for a question, Jim. So, are there any questions in the audience for Jim? Okay, Mike, hold on one sec.
Thanks, Jim. A good overview of where sensors are.
Thank you.
Are your absorbance monitors available in different wavelengths?
Absolutely. We can do 220 nanometers up to 900, and we have a lot of people doing 260, 280, 540. And we actually have one product you can do every 1 second. It switches wavelengths. So through one sensor, you can actually do two different measurements of two different wavelengths. And there's two separate outputs.
Does that have two LEDs then?
Yeah, absolutely it does. It switches every 1 second.
That's pretty cool.
Yeah.
Hi, Jim. Good to see you.
Oh, good to see you.
Are you guys working on a pH meter, or have you decided to give up on that for now?
Well, it's kind of interesting. We probably get, particularly trade shows, but in general, we get that question at least once a week. And the pH technology has pretty much gone full circle. There's many companies that have tried solid state, again, gamma compatible, and they pretty much all failed. I mean, companies have spent many millions for a solid state pH sensor. It's gone full circle back to electrochemical probes that are basically gamma compatible, pre-calibrated, and companies like Hamilton and Mettler are offering those. We are working on some things, and we haven't given up. We're looking for the right partner to work with. But we have the problem with purification operations. You need a very fast response, and a lot of these other technologies, they don't respond quickly. 30 seconds could be too late in a chrome process. So it's really that response time that has hurt a lot of other technologies, as well as other things. So we are working on things, but nothing specific to talk about here.
All right. Thanks.